Electric field on the equatorial line of an electric dipole. To find the electric field on the equatorial line of an electric dipole, let us consider an electric dipole of length 2a and center point 2. The distance of each charge from the center is equal to a, hence the total distance appears to be 2a. Let us imagine a line drawn from the center perpendicular to the dipole axis, which represents the equatorial line. Now, if I consider a point which is at a distance r from the center of the dipole, and we have to find what is the net electric field at this point. Let us call this point as M, and electric field due to the positive charge at point M to be found out, and electric field due to the negative charge at point M has to be found out. The equatorial line makes an angle of 90 degrees with the dipole axis. Hence I can use Pythagoras theorem to find out what is the length AM as well as BM. Therefore, AM squared is equal to AO squared plus OM squared. Therefore, AM squared is equal to A squared plus R squared, or AM is equal to A squared plus R squared raised to 1 by 2. The same can be considered for length BM also. Next, electric field at M due to the positive charge is 1 upon 4 pi epsilon naught q by r squared, where r represents the distance from the point to the charge. Therefore, electric field due to the positive charge is 1 upon 4 pi epsilon naught q upon r squared plus a squared raised to 1 by 2 the whole square, which results into 1 upon 4 pi epsilon naught q upon r squared plus a squared. And the electric field due to the positive charge is pointing outwards. Now the electric field at M due to the negative charge is E is equal to 1 upon 4 pi epsilon naught q upon distance MB, which is r squared plus a squared raised to 1 by 2 the whole square, which is 1 upon 4 pi epsilon naught q upon r squared plus a squared, which is directed towards the negative charge. We find out that the magnitude of the electric field due to the positive charge as well as the magnitude of the electric field due to the negative charge are same in magnitude. Hence, we can say that the resultant electric field should bisect the angle between the two electric fields. Hence, if I now draw a parallelogram, we see that the resultant bisects both in equal angles in such a way that if I assume E to be the resultant electric field, the angle with respect to the positive electric field is theta, as well as with the negative electric field is theta. Hence, I now resolve electric field due to the positive charge into its respective components, where I get E cos theta along the dipole axis and E sin theta along the equatorial line. Also, resolving the electric field due to the negative charge, we get electric field along the dipole axis as E cos theta and electric field along the equatorial line as E sin theta. It is known that the magnitude of both the electric fields are same. Therefore, the components should also have the same magnitudes. Hence, electric field due to the positive charge and sign component and electric field of the negative charge sign component should cancel out each other because they are equal and opposite to each other. Hence, both of them cancel out each other. So we are only left with E cos theta and components of positive as well as negative charges. Now, the net electric field at M is E is equal to E cos theta due to the positive charge plus E cos theta due to the negative charge. So electric field due to both of them now can be found as E cos theta plus E cos theta, where you will get electric field due to the positive plus electric field due to the negative into cos of theta, which is a common factor between both of them. Now electric field due to the positive charge and electric field due to the negative charge are equal in magnitude, and both of them are equal to 1 upon 4 pi epsilon naught q upon r squared plus a squared. Hence electric field is equal to 1 upon 4 pi epsilon naught q upon r squared plus a squared plus 1 upon 4 pi epsilon naught q upon r squared plus a squared into cos of theta, which gives us E is equal to 2 1 upon 4 pi epsilon naught q upon r squared plus a squared into cos of theta. Further, taking alternate angles, if you all check into the diagram, we have alternate angles where angle made by MBO is also theta. Hence, we can say alternate angles are same. And now, in triangle MBO, I can take cos theta is equal to adjacent upon hypotenuse, which gives me a upon r squared plus a squared raised to 1 by 2. Hence, substitute this value of cos theta into your relation. I get E is equal to 2 1 upon 4 pi epsilon q upon r squared plus a squared into a upon r squared plus a squared raised to 1 by 2. Multiply this term inside, I get 1 upon 4 pi epsilon naught 2aq upon r squared plus a squared into r squared plus a squared raised to 1 by 2. We know that x raised to y into x raised to z is equal to x raised to y plus z. Therefore, E is equal to 1 upon 4 pi epsilon naught 2aq upon r squared plus a squared raised to 1 plus half, which is equal to 1 upon 4 pi epsilon naught 2aq upon r squared plus a squared raised to 3 by 2. We know dipole moment P is equal to 2aq. So I get E is equal to 1 upon 4 pi epsilon naught P upon r squared plus a squared raised to 3 by 2. The resultant electric field and the dipole moment, both of them are opposite in directions. Hence, I'll have to use a negative unit vector showing the direction of resultant electric field is opposite to dipole moment. Hence, E is equal to 1 upon 4 pi epsilon naught P upon r squared plus a squared raised to 3 by 2 minus vector P. For a dipole along the equatorial line, we have 1 upon 4 pi epsilon naught P upon r squared plus a squared raised to 3 by 2 into minus vector P. Now for a short dipole, we know r is much greater than a. Now as r is much greater than a, for a short dipole, a in the denominator can be neglected. As shown in the diagram, r is much greater than the dipole length from the center. Therefore, r squared plus a squared raised to 3 by 2 in the denominator can now be written as r squared raised to 3 by 2, which is r cube. Therefore, substitute this value of r cube into your equation. I get, for a short dipole, electric field along the equatorial line is equal to 1 upon 4 pi epsilon naught P upon r cube minus vector